My name is Scott Johnston, and today I am modeling filtration in the glomerular filtration rate for Dr. Malolo's Bio 202 class. What I have here is a drawing of the glomerulus. Within the glomerulus are the glomerular capillaries. These are supplied with blood via the afferent arteriole. The blood comes in, goes across all the capillaries, which is essentially a continuous vessel. Comes out the efferent arteriole. All the glomerular capillaries go through the glomerular capsule, also known as Bowman's capsule, which is lined with the capsular epithelium, and that's a bunch of simple squamous cells. Then we also have the visceral epithelium that lines the capillaries themselves, and these are called podocytes. We'll get a little more into those in just a sec. And I was curious, this isn't part of this project, but I wanted to know the stuff going down this way, what is it? And this is the proximal convoluted tubule, and that's like a lot of reabsorption of like nutrients that comes out that the body doesn't want to waste just yet. So I got a dissected view right here. We'll take a closer look at the podocytes and the capillaries themselves. So you can see my close-up view of the dissected view. We got our capsular epithelium here, but here's our podocytes, on either side, and that's their nucleus. Now these feet-like projections, they're called pedicels, and they go down the sides here too, but these anchor the podocyte to the capillary. And within the capillary we have endothelial cells. These endothelial cells have pores, or fenestrations. These are fenestrated capillaries. With these fenestrations, along with the filtration slits, we have filtration slits listed here, and these are located in between the pedicels. So whatever goes through has to be really small to get through this stuff. So typically like amino acids, glucose molecules, but proteins typically don't get out. Waste will get out. But and then we have the mesangial cell. The mesangial cell has actin-like filament in it, and it allows it to contract, and it essentially helps control the diameter of the capillaries themselves. And now we're going to talk about the pressures involved in glomerular filtration. So the stuff, all the blood in the arteries, I got my blood vessel a little different just to give me some space in here, but it's essentially the capillaries are still in here. But the capillaries pump out filtrate. Now this happens with 55 millimeters of mercury hydrostatic pressure. So that's stuff pushing out of it's pushing stuff out of the capillary. Well, this filtrate that comes out has its own hydrostatic pressure, and so now that acts against the hydrostatic pressure out, and it pushes stuff back in the capillaries. But I got like some figures working with. These are estimates, but they're close. It's kind of close to what the book was giving to. It's 55 millimeters of mercury out, but the filtrate has 55 millimeters of mercury in. So we have essentially a net hydrostatic pressure of 40 millimeters of mercury out. Now we'll look at colloid osmotic pressure. Now that's caused by suspended proteins in the capsular space, but like I said before, proteins don't usually make it out there, so it's not uncommon to see this at 0. So I used a number of 30 millimeters of mercury. That still gives us, a net of 10 millimeters of mercury out. That's our net filtration pressure. Net filtration pressure is pressures favoring filtration, such as hydrostatic pressure out, minus pressures opposing filtration, which is colloid osmotic pressure. Which brings us to glomerular filtration rate. Glomerular filtration rate is the amount of filtrate the kidneys produce each minute. Each kidney has approximately 64 square feet of filtration surface, meaning glomerular filtration can average around 150 milliliters per minute, which is 10% of the blood delivered to the kidneys, is delivered to the Bowman's capsule and goes through the filtration process, which speaks volumes about the filtration power of the kidneys. So that's all I have on glomerular filtration rate today. I hope you enjoyed it.